Okay. So apologies that we didn't do this earlier and we missed all the fMRI prep on the recording. So if you need help on fMRI prep, talk to Kelly. But we are going to record this section on neuropathy, I guess. So yeah, we just opened up a notebook and imported neuropathy. I'm going to hide this to make a little more room. So we already saw this example. And in fact, I'm just going to jump over to the NSD. Sorry, I'm just going to go to the NSD notebook that we literally just were looking at in the last session, because there's a little bit of code here that grabs a free surfer subject out of the NSD somewhere in here, right here. Okay, rather than have to reproduce that line. But I'll wait a minute so you can all copy that down if you want to follow along live coding here. So basically, now this can be a directory on your computer, and that's how it's typically used, is that you point it at your free surfer subject directory and you just give it a path to a subject. And in fact, if you've got free surfer set up on your directory with like a subject stir environment variable, you can just say free surfer subject BERT and it'll give you back the BERT subject or whatever it knows about subject directories. Regardless, when we ask NeuroPython to give us a free surfer subject, it gives us back a subject object, like a Python object that is a subject type. Let's just start by looking at some of what the subject has in it. So you'll know about the dir function in Python. It'll list all the members, the methods and members of an object. So if we do a dir on this subject object, first of all, you can see LH and RH for left hemisphere and right hemisphere. Then there's a bunch of these double underscore things that are like kind of private Python things. And then there's several other methods and variables. So there's things about image dimensions and image addresses, which I'll talk about in a second. There's metadata, there's some parameters, there's normalization functions. There's gray indices and a gray mask for both left and right hemisphere. These are just kind of various utility things that are attached to the subject object. Yeah.
So these are all just the defaults that come out of the free surfer object?
So everything here can be derived from free surfer. Yeah.
Okay, so you just give it the subject folder, right?
Yes.
Not specific output from free surfer.
Correct. Yeah, you give it the subject folder and it goes and it will organize everything from those folders for you. And the idea is that if you're using NeuroPython, you should never really have to go look inside the free surfer subject folder, because it's hard to interpret inside there. So let's look a little more closely at a hemisphere. So I'm going to do sub dot left hemisphere. I'm going to make this a little bigger and hide this. Now you notice there was sub dot LH and there's also sub dot LH lowercase. They're the same thing. They're just aliases for each other. Oh boy, if we're getting an error, that's not good. Oh right, I'm not in Mathematica, I'm in Python. So they are the same thing. Yeah. Okay. So if we just take a look at the left hemisphere, first of all, the left hemisphere has many different surfaces attached. So there's this dictionary, or a kind of, this is a type of dictionary basically, that contains all the different surfaces. So if we just do a list of the keys of this dictionary, we see things like peel, white, mid-gray. White original is the very first surface that free surfer produces before it does post-processing to make it nice and smooth. Inflated is, of course, the inflated hemisphere, and then there's the spherical hemisphere. Do you all know what I mean when I say the spherical hemisphere? Okay, I see mostly nods. Some of you say no, so I want to show you another fun animation that might even be in this talk. It is. Okay, so conceptually, you can think of a hemisphere as a sphere because it doesn't have any holes in it. So what I think free surfer did that was really important, I mean, there were a lot of things. It wrote this segmentation algorithm that everyone uses, and that's very important. But the thing that I've gotten the most use out of from free surfer is this notion of anatomical alignment based on the surface. So what we're seeing here on the right is an actual human hemisphere. On the left is the FS average hemisphere. So the left is actually the cortical surface model you get when you average like a bunch of people together, a bunch of brains together, and then make a surface model of that average. So what FreeSurfer realized is, first of all, if we want, what we want to do is we want to come up with a correspondence of points. So if we pick a point on this cortical surface, we know what is the anatomically closest point on this average surface. So to do that, they said, well, it's easier to work with things if we just start by inflating them into spheres. So here we have spheres, and that mathematically is much easier to deal with. So that said, if we were to highlight like the calcarine sulcus right there on the average brain, and we were to put that in the exact same position on the actual brain, it doesn't quite line up with the calcarine sulcus. It's not crazy off, but based on like the orientation of my head, it might be in a different position. And so they're not aligned. Now, we could take a very simple approach and just do like a rigid body rotation of the sphere until they were aligned, but that would align this ROI and not other ROIs. So instead they said, let's treat the human brain as a great big piece of rubber that you can stretch and compress. You can't fold it and you can't tear it, but otherwise you're allowed to stretch and compress individual parts kind of on their own. And they did a great big optimization where they tried to get the curvature pattern on the right to optimally match the curvature pattern on the left. That looks like this. So you can see that was like, there was a bit of rotation in there, but it was like a diffeomorphic kind of warp field that they applied. And after that's been applied, we have this really nice alignment between the curvature pattern on the right and the curvature pattern on the left. And so we have, that basically gives us an anatomical correspondence where this point here corresponds to this point here. And if we now align another brain to the average, we have a correspondence between those two individual brains. That all make sense? Any questions? Okay. So that's kind of one of the cool things that FreeSurfer did, and that's why we have the spherical brain or the spherical surface. That said, the spherical surface is not the aligned surface. That is what's called the FS average surface. There's a historical reason why it doesn't show up in the surfaces list here, and that's because it's in what's called the registrations list. And you'll notice that there's other things in here, many of which I've made. But the FS average registration is the sphere registered to the FS average brain. So you can actually use, and this is kind of important, because we have an FS average registration for this subject, and because if we load another subject into NeuroPython, they'll have an FS average registration, which those registrations were produced by FreeSurfer, not by NeuroPython. NeuroPython just reads them. But that means that if we have another subject and we have data for that subject, like a retinotopic map or really anything, a curvature map, we can interpolate from this subject onto this subject and back and forth. And so we can compare them to each other using this kind of anatomical alignment. Does that make sense? Okay, so let's, and interrupt me if you've got questions. I'm just going to keep talking. Yeah.
Can you also work with NeuroPython in subject space?
Yes, so NeuroPython is designed to work in subject space, really. And the idea is you use FS average to get data from one subject to another, or from one subject to an average, but you don't generally operate in FS average space if you don't have to. Yeah. Yeah. So in general, I always prefer to work in subject space. If I don't have to transform the data, I don't. Yeah. Okay. Again, interrupt me if you've got questions. I'm just going to keep kind of telling you things that I think are cool about the brain. So if we, so obviously we saw this cortex plot function, and I think I refer to this a little bit. I'm going to go ahead and plot. Let's plot the peel surface for a change. So cortical surfaces, this is something I really think ought to be taught a little better in neuroscience courses, but like when we look at these cortical surface models, they're produced from the segmentations of the gray white matter boundaries, or the gray matter and the white matter, and from the boundaries between them. But what FreeSurfer actually does to produce these models of the cortical surface is go along and tessellate the boundary, which means it turns it into a big triangle mesh where there's a bunch of vertices on the cortical surface, along with a bunch of triangles that connect them. So if, it doesn't necessarily look like that right now, but if we zoom in really close, you can see the individual triangles that make up this mesh, and they're pretty clear here. And so really the way that the surface is represented is nothing like voxel space. We have a list of vertices that is associated with the surface, each of which has a 3D coordinate. And then we have a list of triangles, each of which has corners that are vertices in the vertex list. So,
Sorry, maybe just something.
yeah,
So when you actually, just to connect that with the FMI prep, when you actually request FMI prep to project your functional data onto the surface, you will be inherently inheriting some redundancy in its interpolation from voxel space to vertex space, because there are always going to be more vertex than there are voxels. And also additionally, based on the way the researcher does their volume to surface kind of thing, you might have an overrepresented voxel sampling in some particular locations of the brain than others. So that is something else to be mindful of as well.
yeah. So this kind of comes down to the resolution of your mesh versus the resolution of your voxels. So in theory, you could have a higher resolution mesh or a higher resolution image, but typically we try to match the resolution of the mesh to the image as much as possible. And you'll always have more vertices than more vertices in that case than voxels in the ribbon, as Kelly said. Okay, what was I going to say? These vertices and indices or triangles we can actually just find in the surfaces. So if I get the subdot left hemisphere and I ask for the Peel surface, I can then look at the surface coordinates, and that's just a 3x(n) array of the vertices. I can look at the surf. There's a whole sub-object in the surface that's the tessellation data. So this includes things like the faces or the triangles. And you'll notice that the faces is a 3x(n) array of integers. That's because it's telling you which vertex is at each corner. So this right here, this first column is one triangle, and it contains vertices 0, 1, and 3 as the 3 corners. And so we'd have to go back up to the coordinates and say, okay, here's these first numbers are 0, these ones are 1, and then 3 would be the first one in this ... And those are the 3 of the XYZ coordinates of the 3 corners of the triangle. Does that all make sense so far? Okay. Something, let's see, I don't know if I'm getting too in the weeds here, but something about the way that we represent triangle meshes is that by convention, I'm actually going to draw something on the board, so apologies to Zoom people if this is hard to see. By convention, you have 3 vertices that form a triangle in a mesh. You can list like in theory, we can list these 3 vertices in any order and we have the same triangle. But there is one difference that matters, and that's whether we list them in clockwise or counterclockwise order. And the reason that matters, it actually doesn't matter, but it matters in the sense that if you want to tell whether a point is inside or outside of the surface, that's a really hard problem to solve. That's actually pretty hard to solve, even if I just give you like a 2D polygon and you're trying to figure out whether some point is inside the polygon or outside the polygon. So in order to make that problem easier, we always specify triangles in counterclockwise order relative to the outward pointing vertex normal. I don't know how much you all remember cross products and yeah, the right-hand rule from trig, but the basic idea is if your triangle is listed in the order ABC, then AB is one vector, BC is the next vector, and if you cross product them, the vertex that you get in the cross product should always point out of the mesh. That ends up being important more often than you think if you're doing like low-level surface analyses, because you often want to know things like whether or not a vertex is inside or a voxel is inside the surface or not. Another place that ends up coming up a whole bunch is in vision. We talk about the visual field sign, but I won't go into that right now. It's a concept of whether or not visual areas are organized as a reflection of the real world or as a kind of image of the real world. Anyway, okay, questions so far? I think I'm getting too in the weeds, so I'm going to come back up in a second. Okay, So surfaces and hemispheres also have properties, and these are kind of probably more interesting to all of you. So let's suppose we wanted to look at the gray matter thickness of a subject. So I'm just going to take our subject's left hemisphere again. I'm going to plot the inflated surface this time, and I'm going to color it according to the thickness. And thickness is just a property that FreeSurfer calculates. It's the gray matter thickness at every vertex. And I'm going to use a hot color map. And in fact, because the gray matter thickness tends to vary between about 2 and 6 millimeters, I'm just going to have a minimum and maximum of 2 and 6. This will take just a second while it downloads the inflated surface and the thickness. But you'll notice that I just passed a string there for the color. And that's because thickness is a property that's already attached to the hemisphere in NeuroPython. And while this loads, I'm going to go ahead and talk a little bit about this. So in addition to like the surfaces dictionary that we saw, oh, there it is. So this is gray matter thickness. You can see that here in the corpus callosum, there's basically 0 thickness because there is no thickness there. You can notice that in the posterior cortex, near sensory cortex, there's thinner cortex in general than up in like frontal cortex. But this is basically the gray matter thickness. Okay, so there are properties. And I'm just going to give us a sorted list of the properties here. So properties are attached to every hemisphere, and you'll notice that there's like Brodmann area labels and Brodmann area weights here. And then there's an MT label. There's the curvature of the FS average atlas. There's more Brodmann labels. There's various data about FreeSurfer's pre-processing steps, like the Jacobian norm is about that alignment step. But there's also like PL curvature, and somewhere in here should be thickness and the white curvature and the surface area of every vertex. So these are just things that are attached to the hemisphere, and we can plot any of them. And in fact, we can always plot. We can always plot these by actually passing the color. So, for example, we could say sub.lh dot property thickness, and we'll get the same thing, although with a different color map this time because I didn't pass the color map. And this is just all this is. If we were to, actually let us look at that. All that is a vector of values, 1 per vertex on the mesh, and for each vertex, it gives us a thickness at that vertex. And this reminds me, here we can see it. Yeah. So this is using a much more colorful color map, but you can see that there's kind of a similar pattern of thickness with low values and higher values. But this reminds me that there's something very important and many people find unintuitive about these meshes. If you're used to working in voxels, you can guarantee that if you have voxel ijk, you know something about voxel ijk plus 1 and about I plus 1 jk. They're next to each other, right? With meshes, you have no such guarantee. The order of the vertices on a FreeSurfer mesh are determined by some arcane algorithm, and there's no guarantee that vertex 1 and vertex 2 are going to be next to each other. They could be on opposite sides of the brain. The only thing that tells you about how close things is the triangle mesh. So if you want to do things like average across neighbors or something like that, it can be very tricky. I'll just mention along these lines that it's important enough that NeuroPython actually, in this tessellation data structure, calculates what's called neighborhoods. I hope that works. Basically, for this is a list or a tuple in CatFact with as many, like basically it's a tuple of tuples, and there's a tuple for every vertex on the mesh, and it's just listing the neighbors of that vertex. So this first one is vertex 0, and vertex 0 is adjacent to those 5 vertices. And vertex 1 is adjacent to these 6 vertices, etc. And you can see that although like these are mostly low numbers at the beginning, there's not like rhyme or reason here. Like this vertex is next to 83, 319, 311, 312, and 75. There's not any significance to the vertex number really. It's just the vertices are almost like randomly tessellated across the cortex. Okay. What questions do you all have so far? Okay. Each row? Yeah, so each row is basically the idea is that you would ask for like row K, and that would give you a tuple. Whoops, why did that? Oh, of course, because I haven't defined K. So let's just ask for row 10. These are the vertices that are adjacent to vertex 10 in the mesh. So you don't. 10 is the 10th vertex in the vertex list. That's kind of the irony here, is that because meshes are very irregular, they're not like images where you've got voxels that just stack on top of each other. Meshes are irregular, so the tessellation algorithm has to come up with some way to put vertices on the mesh. But if you just think about it, any method you try to use to put vertices on a mesh, maybe you want to spiral out from a point, or maybe you want to go around the mesh and then go around another way or something. Like all of those are going to produce some weird set of vertex neighbors. So basically, you just kind of have to give up on the notion that the vertex number means anything. It doesn't. The vertices may as well be in the random order.
And then all the numbers, like I ran up to 10, so that's fine.
Mhm.
But can you then like now how I'm going to bring like the very small?
Oh yeah. Yeah, so vertex 10. So this is kind of, and honestly, this is the kind of tricky thing about surfaces that a lot of people have trouble with, is that when you store surface data, you just store a vector of values, and the values are just by convention in the same order as the vertices in the coordinates matrix. So vertex 10 is vertex 10 in every piece of NeuroPython data for this subject in this hemisphere. So if I want to know the coordinates for vertex 10, I ask for the white surface, for example, and I get the coordinates, and I say, what are the coordinates for 10, vertex 10? This coordinates matrix is a 3 by n, so that's why I do colon, comma 10.
But I guess we can also like read from the label, right? Label file.
Yeah. Yep. So label files contain vertex numbers, exactly. And those will tell you which vertices are in a particular label. Yeah. Yep. Other questions? Okay, we've got a couple more minutes. Trying to think if there's anything especially fun in NeuroPython that I can show you in less time. Yeah.
Can you show how to create a platform?
Yes, I can do that. Okay, so NeuroPython has a function called toFlatMap. This is a little funny. In theory, so I wrote this function to use what are called map projections, which are basically, you tell it like, here's a particular, you know what, let's ignore this function. I'm gonna try this a different way. There's a function that is part of the hemisphere, and I think it is called, oh shoot. I'm gonna have to go look at it. It's something like mask flat map. It is mask flat map. Okay. So basically, let's suppose we want a flat map of V1, and I want a flat map of V1 because that's what I always want. We can say we want a flat map that's based on a mask, a particular mask. And in this case, the mask is the vertices in V1. So NeuroPython has a little like mini way to represent masks in general. And we saw a little bit of this earlier when I made a plot that said PRF variance explained between 0.1 and 1. You can give it just a property like V1 label that is Boolean. So the V1 label property is already a property attached to this subject. And if we were to look at it, it's just false everywhere that's not in V1 and true everywhere that's in V1. So I'm just going to give it the V1 label and say, I want a flat map where this mask is in the center of the flat map. I'm going to tell it that the method of projection I want to be, let's say, orthographic. So what it's going to do is it's going to inflate, it's going to take the inflated sphere, not the aligned free surface average aligned sphere, but the native inflated sphere. It's going to put the V1 label at the center, and then it's going to make an orthographic projection. And I'm also going to say that I think it is map right equals right. So what I'm saying there is you can make the projection, but V1 could be oriented like this, or it could be oriented like this, or whatever. And so I'm saying I want right in the T1 to be on the right side of the map here. I hope this works. So I'm going to capture this as fmap. And then the cortex plot function actually works just fine with fmap. I'm going to tell it to color it red wherever the mask is equal to V1 label. And when you do a plot like this with a 2D map instead of a 3D map, it uses matplotlib to make the plot. So we can just do plot.gca dot what's the axis equal? Like this, I think. So this is probably taking a minute. Okay, yeah, it probably took a minute because it had to load some stuff. Oh, I haven't imported matplotlib. And there we have a flat map of cortex, and I can maybe make that small enough that you can see it with V1 highlighted. So that's a way to do it. Yeah. Yes. Yeah, and there's so since we don't have a whole lot of time here, I'm just going to also point out that while the online documentation for NeuroPython could be better, the internal documentation is generally fairly good. So if we just ask for help on this function, it's got at least a little bit of details about all the different arguments. So for example, if we want to, of course, this is just telling us to look at the macro projection function, but basically the internal documentation that you get in this kind of method is generally better if you're looking for things. But I'll read that and let you see this again. Other questions? Yeah.
So is there a way to take, so some of the applicants could over to like an atlas or something?
Yep.
Like the 2009.
They're the APARC, ASAG, yeah.
Is there something that overlays those masks into another volume or something like that?
Oh, onto a volume?
Yeah.
Okay, so if you want those something like that, so that parcellation is a property in NeuroPython, so it's just a property with label values for every vertex. What you would want to do is there is a function cortex to image, and basically this says if you've got data on the cortical surface like a property and you want to put it into an MR image or like a volume, basically I'll say sub.lh.prop, and I am going to need to check what it's called. I wonder if I still have that list of properties up here. Whoops. Yeah, so I think it's called Destrio09. Yeah, this is the name of that parcellation. So we want to pull out that property. We want to do that. We want to give it both the left and the right hemisphere because we want to make a volume. Except this needs to be right. And then we need to give it a template image, but in this case, we can just, the subject also has all the images, so we can say we want to use the brain as a template. Capture it. Now, and because these are integer values, I think it will do this automatically, but we don't want to use linear interpolation. We want to use nearest neighbor interpolation for integers. Now I have a prediction about what this is going to do. I think it's going to do something kind of funny, but you'll at least get the idea. If we then were to just take something out of the middle of this image. Oh, I'm almost out of memory too. Oh, yeah. Yeah, unfortunately, these kinds of data are a memory beast. Well, let me see if I can just rerun those last couple. This will probably have to re-download the data now, but anyway, what this function does is it gives you back an image with the same orientation as this template image, but where these surface data have been projected into the gray matter ribbon. Yeah. So, and to be honest, I use this instead of free surfers, surf to vol, and vol to surf because, to be honest, I suspect free surfers, surf to vol, and vol to surf are fine these days. But back when I wrote this, the algorithms were not very good, and they would leave great big holes in the surface and the volume and stuff. And so this will not do that. This will fill in the whole ribbon, and it does it pretty well.
I would say that the algorithm is better, the call is a nightmare.
Yes.
This is much cleaner.
Yeah. Yeah.
We could actually extract value from that.
Oh yeah.
Okay.
Yeah. So this gives you back a nifty, like a knee-babble nifty image object, and you can just save it out to disk if you want. Apparently, it takes 8 gigabytes of memory to do this. That's too bad. Well, you'll have to trust me that this works. Sorry. Okay. Any other questions that I can answer before? I think we're basically at 5 o'clock. So, and it's Friday. Thank you all for staying past 4:20.
Sorry, is it possible to upload the slides?
Yeah. Okay.
Oh, those other slides. Yes, you can also just watch that presentation in the 2020 NeuroHackademy. Those are keynote slides, so and it's got a bunch of animations in them. So if I upload them, they won't be very satisfying. But yeah, those slides are a useful introduction to MRI geometry and some of these file format kind of issues. So yeah. Okay. Well, thanks everyone, and I hope you all have a good weekend, and we'll see you on Monday.